Hi folks, and welcome to our Chapter 5 pre-recorded lecture. Today we're going to be talking about different kinds of chemical reactions. So what's going on here is we're going to start talking about how different atoms will make and break new bonds, or will make new bonds by breaking old bonds, forming new products. So the idea here in a very abstract way is showing two different types of molecules undergoing some sort of reaction to form brand new products. So in terms of how we will represent this kind of reaction is we use something called a chemical equation. You can kind of think of it in the same way we use a math equation. There will be math involved with this as we get going, but chemistry kind of uses a lot of extra little pieces to it. So for example, on the left-hand side of this arrow we can pretend is kind of like an equal sign if we were doing a math equation. To the left of the arrow will be the reactants. These are the things that we originally have, the materials that we start with. And then the equal sign is chemistry occurs. And the products, or the things on the right-hand side, are the new things that are formed. Couple different things we need to kind of address here is, one, we're going to pretty much always use the symbol of the element or molecule that we're writing. Another really important thing that we're going to have to start doing is utilizing these guys right here. These are the states of matter, so solid, liquid, gas. We'll also talk about something called aqueous that we represent with AQ, and that's a special kind of solution, a solution that is dissolved in water. So products, reactants, and we're going to talk about these crazy little numbers in a second. So again, products are going to be the substances that are produced. Reactants are the substances that are undergoing a change. When we have two or more reactants or products, we're going to separate them by a plus sign. So one of the really important things that we need to talk about here is the law of conservation of matter. This is a very important concept. It basically means that we can't create or destroy atoms. From the reactants, we can only have that many number of atoms coming out of the products. Now, number of atoms is different than number of molecules. For example, down here we have H2 gas and O2 gas giving us liquid water. There are two things over on this side and only one on this side. But if we start going through, we can actually see that this will be a balanced equation. No new atoms were formed. The way this is done is through ratios. You could think of this in the same way that you cook like a recipe for cookies or something like that, right? Let's say it's 1 cup of sugar to 4 cups of flour. That's a ratio of 1 to 4. We have ratios that we are going to represent in our quote-unquote balanced equation, or our recipe to make water in this case. For every 1 unit of our oxygen, we're going to need 2 units of hydrogen. Now, few things we need to talk about in this. Remember, oxygen, hydrogen, these are our diatomic elements, right? We know that these exist in nature as diatomic molecules, right? These are elemental molecules. It's never going to be oxygen as a single O by itself, and it won't be hydrogen as a single H by itself. They'll always exist as O2 and H2. So that means we have 2 atoms of hydrogen and 2 atoms of oxygen. And they're forming H2O. We know H2O is water. Now, we have these 2's in front of the H2 and a 2 in front of the H2O. And these are where those ratios come in. This is saying we have 2 H2's, right? 2 H2 molecules, and that we form or produce 2 water molecules. So when we go through and look at this, let's check out how many atoms of each thing we have. If I have H2 and I have 2 of those, that would mean I have a total of 4 hydrogen atoms. And if I have no number in front of my oxygen here, we can pretend it's a 1. If you need to write the 1 to kind of do bookkeeping for yourself, that's totally fine. So I have 2 atoms of oxygen. Let's look at the product side now. I have 2 H2Os. So we know in one H2O there would be 1 oxygen and 2 hydrogens, but now I have 2 of them, which means I would have 4 hydrogens and 2 oxygens. That means that on the left-hand side and the right-hand side, I have the same number of atoms going in as I have coming out. And that would be a balanced equation. So let's look at this in a little more in depth. If we were to look at something like a combustion reaction, so a combustion reaction, the way we're going to learn it will be any type of hydrocarbon compound. Right now you don't need to know that this is methane. In a couple weeks you will know why CH4 is called methane, but for right now we just have this CH4 compound. Anytime a CH4 compound is combined with oxygen and the products are CO2 and water, regardless of, like we talked about those coefficient, those numbers in front here, regardless of those, this will always be a combustion reaction. Combustion reactions are always hydrocarbon plus oxygen yields or equals, in chemistry we say yields, CO2 and water. Always, always, always. In a little bit, we'll also talk about the fact that this also generates heat. But explosions generating heat, hopefully that doesn't sound terribly surprising to you. So methane, the main ingredient in natural gas, will combine with oxygen when it burns, forming carbon dioxide and water. It's written like this. Now, if we were to just go through real quick and look at this equation, we'd say, okay, I have 1 carbon on my reactant side, I have 1 carbon on my product side. So far, so good. I have 4 hydrogens on my reactant side. I only have 2 hydrogens here, so I already know, without going into too much depth, that this is not a balanced equation. And so I'm contradicting the law of the conservation of mass and matter, so I know this can't be right, so I'm going to have to go through and balance it. So again, these little tables are a really nice way to kind of set them up to help you figure it out. So again, you can do some of it in your head, especially when you start doing your homework. There will be ones that are fairly in-depth that you're probably going to want to write out. So basically you want to start off by having identified what atoms are on both sides. In this case we have C's, H's, and O's. Then we have a reactant side and a product side. And then you go through and figure out how many of each you have to start off with. So we have 1 carbon on each side. We talked about that already. We have 4 hydrogens on the reactant side. We only have 2 on the product side. And then we have 2 oxygens on the reactant side. And we have 1, 2, 3 oxygens on the product side. So the H's and O's in this case are not balanced. So we're going to have to come up with a way to balance this. So we start needing to look at ways that we can manipulate those coefficients. And this is kind of one of those things where, start with one thing and you'll go back and forth and have to adjust for it. So in this case, if we put a 2 in front of the oxygen and a 2 in front of the water, when we go through and recount how many atoms of each thing we have, we didn't affect our carbons. Those are both still 1s. Our hydrogens now, we have 4 hydrogens on this side still, but now we have a 2 in front of our H2O here. So 2 H's here. This is going to be a total of 4 hydrogens now, so that's now balanced. And then when we look at our oxygens on our reactant side, we now have 4 oxygens here, and we have 2 on the product side from the CO2, and we have 2 from the H2O. So we now are able to say that we have 4 oxygens as well. This is now a balanced chemical equation. We will talk a little bit later in this section about why a balanced chemical equation is so important, especially when we start talking about things like figuring out how much of a product we make. If I know how much of this material goes in, I can figure out and calculate how much product will come out. Or I could know how much product is made, and I could determine how much product or reactants went in it, and vice versa. So I want you to try this one on your own. This is a hard one, and you should start being comfortable with the idea that sometimes you're going to just be given the words of a compound, right? So it is expected that you're going to know your nomenclature, right? This idea of how to name things. So it's really important that we be able to kind of write out the chemical formula of those. But for right now, I'm providing it for you. So I would really encourage you to pause the video right here and give this a shot on your own, and then we'll go through it together. So I'm going to pause for a sec. Okay, hopefully you've tried this on your own, and so we're just going to go real quick through how you would solve for this. So if we're given nitrogen dioxide is an air pollutant that is produced in part when nitric oxide reacts with oxygen gas. So the first thing we would need to do in a word problem is determine what are the reactants and what are the products. Oops, sorry about that. So we know that, oh boy. There we go. We know that products will be, whoa, oh no, that is backwards. Look at that. Let's change that right now. Reactants. See, look, we're learning all the time. Reactants are on the left, and our products are on the right. So when we look at this kind of word problem that we have up here, we have to determine which ones are going to be the reactants and which ones are going to be the products. So in this case, we're told that nitrogen dioxide is produced. So the nitrogen dioxide is our product, and nitric oxide and oxygen gas are our reactants. So we're going to have something that looks like this. Again, don't forget your states of matter. And if I didn't tell you it was O2 gas, oxygen gas, diatomic. Okay, after that we need to determine if this is already balanced or not. So we're going to go through and determine what atoms are on each side and how many of each we have. So we have one nitrogen on each side, however we have 3 oxygens on our reactant side, and on our product side we only have 2. So we are not balanced, so we're going to have to go through and figure out a way to balance this. So we need to do this by balancing and adding coefficients. So when we look at our possibilities here, we see that the nitrogens are balanced, but the oxygens weren't. So if I started adding oxygen's coefficients here, I'd be adding them by 2, so it would increase this by 2 each time, right? So it would go 3, 5, 7, so on and so forth, which would be really hard on this side to somehow get that number to match that number. So when we look through these logically, there's a lot of trial and error with these. So we're going to try going with our nitric acid and our nitric oxide, or excuse me, our nitric oxide and our nitrogen dioxide as a way to manipulate the coefficients to balance out the chemical equation. So if I go through and add a 2 on the nitrogen oxide, or the nitric oxide side, I now would have 2 nitrogens, and I would have a total of 4 oxygens on this side. I still have 2 from my oxygen gas, and I will now have 2 from the 2 NOs for a total of 4. On the product side, I now have 2 nitrogens, which balances that out still. But I still only have 2 oxygens on this side, or excuse me, I still would only have 1 oxygen on this side now. So if I added 2 here, that would balance that out, and if I added 2, that will give me 4 oxygens as well. And now I have a balanced chemical equation. Your homework will be a lot of really good practice with this. Again, these are right out of your textbook. I would encourage you to give these a shot. Your homework will help tons of practice with this as well, but the more, the better. So we're going to have kind of take a break from doing balancing chemical reactions to talk about different kinds of reactions that can occur. We actually already talked about one of them when we were talking about combustion, which is often a combination type reaction, but we've already, this kind, talked about it, but we're going to talk about it in more detail. There's two general flavors of chemical reactions. We have redox reactions and non-redox reactions. And under those flavors, we have things like combination and decomposition. Those probably seem pretty straightforward, things adding together or things breaking apart. And then we also have these concepts of single replacement and double replacement. Depending on the resources you are using, this might be called single displacement or double displacement. They mean the same thing. It's just a matter of where you're getting your resources from. So redox reactions are a little tricky. Your books goes into some pretty good detail with this. We also have in the resources, Unit 1 resources section, a much more in-depth kind of PowerPoint presentation on redox reactions. The word redox is actually a combination of two different words, reduction and oxidation. And basically, these are words that kind of tell us something that's going on in a reaction. So, an oxidation reaction would be something where, one, it typically combines with oxygen. We lose a hydrogen, we lose an electron, or we increase an oxidation number. We'll talk about this last one a little bit more as we get going. A reduction reaction would be to lose an oxygen, to combine with hydrogen, to gain electrons, or to decrease an oxidation number. And while these might not make a whole lot of sense to you right now as I'm talking about this, hopefully what you did notice between oxidation and reduction is that they're opposite of each other. So just like we talked about in our previous lecture where we discuss things like the give and take of electrons, right? If something is giving up the electron to form an ionic bond, then something else is taking it on. If there's an oxidation reaction occurring somewhere, the reverse or the other side of it, the reduction reaction, is also occurring somewhere in that chemical reaction. So we talk about this increase or decrease in oxidation number. Oxidation number, also called oxidation states, again, depending on the resource that you're looking at. In our textbook, they abbreviate it as ON. So if you're reading and you're confused what the heck ON means, they're just talking about the oxidation number. And the oxidation number is kind of a way that if these are used when we have covalent compounds, but it's kind of like a way pretending, what if it wasn't covalent, this covalent compound, even though they're sharing them, if they were like to get a divorce and no longer be sharing those electrons, who would have like custody of those electrons? And that number of electrons is kind of the oxidation number. That's one way you could kind of look at it. So the oxidation number will either be positive or negative. Again, remember, these are covalent compounds, so there's no real charge, right? But this positive negative thing going on is just kind of a way to keep track of how many electrons are being moved around through the bonds. And so there's a couple of rules that help guide things. So for the most part, these are fairly hard and fast. There are a few exceptions. Your homework, you will see more of the exceptions. On your tests and quizzes, I make an effort to try and make it more straightforward. But on the homework, they could get a little more complicated. So the first rule is any uncombined element will always have an oxidation number of 0. So when we say an uncombined element, what we're going to think about is basically having that element or that atom or atoms in its elemental state. So for example, aluminum, the solid, would have an oxidation number of 0. Oxygen like this, diatomic, diatomic, this is how it exists in nature, this would be 0. So each of the atoms of oxygen in O2 would both have oxidation numbers of 0. Same with the bromine or a sodium salt, or excuse me, a sodium solid atom. The oxidation number of simple ions is equal to the charge on the ion. So if I had something like Na plus or Mg2 plus or S2 minus or something like that, the charge that is on that ion, whether it's a cation or an anion, is identical to the oxidation number. And then we have a couple other ones that are pretty straightforward. So group 1A will have a +1 charge, group 2A will have a +2 charge. So for example, sodiums will be a +1, calciums would be a +2. This falls fairly close in line with rule number 2, but just throwing it out there. For the purposes of our class, when we have a hydrogen bound to anything other than another hydrogen, like in H2, it will always be +1. Just write it down somewhere. Hydrogens combined +1. In the same kind of breath, 95% of the time, whenever we have an oxygen, it will be a -2, unless it's a peroxide. Then it'll be a -1. And lastly, the sum of all the oxidation numbers in a compound must equal 0. So kind of similar to what we did when we were talking about charges on ionic compounds. So for example, here we have potassium chromate, and we're going to go through and look at this. Okay, potassium we know is going to be a +1 charge, but when I look down here, this little guy here tells me that I have 2 of them in my overall molecule, which means I have 2 +1s for overall +2 on the K. And then on the carbon, we can't really figure that one out on its own. We don't have a whole lot to go with based off of our rules, so we're going to hold off on that guy. But now we can talk about the oxygens, and we see 3 oxygens, and we know that the rule is those are going to be -2, so that would be an overall -2, or excuse me, -6, right? 3 and 2 is 6, so -6 and a +2, and this whole thing has to be 0, which means our carbon has to be a 4 plus. Carbon is one of the ones that you're going to kind of have to base it off of everybody else and what they've got going on. This means that the oxidation number of the carbon in this particular molecule is +4. But in other molecules, it might be -4 or -1 or +1. It will change. So it's something that will be dynamic and that you'll have to account for. The last rule that we're going to talk about is the sum of all the oxidation numbers in a polyatomic ion. So if we have an ion where there's a charge associated with it, the oxidation numbers should reflect that charge as well. And so that's what we see here in terms of this. Manganese, we don't know necessarily what the charge is of it. We know it's a transition metal, so it could be kind of all over the place, so we can't really use rule 2. So we're going to go based off of our oxygens. When we look at this, we have 4 oxygens. Each oxygen would be a -2 for a total of -8. But we have a minus charge here, right? This is a polyatomic anion, right? So it needs to be -1. So if I have -8 and it needs to be an overall sum of -1, my manganese must be +7. Okay, so let's start putting this together now with what we talked about in terms of identifying something as oxidation or reduction, right? We talked about something undergoing oxidation or undergoing reduction, and what that would mean in terms of gain or loss of electrons or oxidation numbers. So let's look at this reaction that we have here. We have sodium solid plus water yielding hydrogen gas and NaOH. Now, let's go through. Whenever you see a chemical equation, the first thing you should do before anything else, because it's going to change and start really, really mattering, is looking and going, okay, is this equation balanced? Now, if it is balanced, great, you can move ahead. But what will really be frustrating for you is to forget to balance an equation and then start doing the math. And then the math doesn't work and you wasted a whole bunch of time trying to work on a problem that is impossible because it hasn't been balanced yet. So always check for balancing first. So we're going to go through and just kind of do the mental exercise in our head. I have 2 sodiums on this side. I see 2 sodiums on this side. I see 4 hydrogens on this side. I count 1, 2, 3, 4 hydrogens on this side. I count 2 oxygens on this side. I count 2 oxygens on this side. All right, I have a balanced chemical equation. So now I can go through and start looking at the oxidation numbers. An oxidizing or a reducing agent is determined by which one is doing the oxidizing and which one is doing the reducing. So an oxidizing agent is the thing that does the oxidizing. A reducing agent is the thing that does the reducing. But remember, this is kind of like that yin and yang thing, right? They're complementary to each other. So if something is the oxidizing agent, it is the thing that is being reduced. If something is the reducing agent, it is the thing that is being oxidized. I'm going to say that again. This would probably be really, really important to write down. The oxidizing agent is the thing that is being reduced. The reducing agent is the thing that is being oxidized. Okay, let's move on. So before we can figure out which is the determining, which is the oxidizing agent, which is the reducing agent, we kind of have to go through and look what happens to each of these atoms as they go through this process. So let's start with the sodium. The sodium on this side is sodium solids. This is in its elemental state. So these sodium atoms on this side would be 0 for their oxidation number. But we see the sodium over here, it's combined now. So we're going to use rule number 3, right? That's the one that talks about either, what its ion would be, or in this case, the group that it's in. So this would be a +1. So that went from 0 to +1. All right, so a change occurred there. That's going to be really important. When our oxidation number changes from reactants to products, it either was oxidized or it was either reduced, and we'll go through that in a second. Let's keep going though. Our hydrogens, in this case we had our hydrogens on this side, they were combined, and we look at it in water, and we know oxygen's a -2, so each of these hydrogens must be a +1. Plus we know that the rule is combined hydrogens are always +1. Let's look on this side. We have hydrogen in 2 different places. We have a hydrogen in the form of hydrogen gas, and we have hydrogen in the form of NaOH. Let's do the NaOH first, because that's the easier one. It's a combined hydrogen, which means this is going to be a +1. So the NaOH, the hydrogen in the NaOH did not change as it went through the process, right? It stayed the same, +1 and +1. But let's look at this guy right here. This is really important. Hydrogen gas, diatomic, that's its natural state, so it has an oxidation number of 0. So we went from +1 to 0. Sodium, we went 0 to +1. Do you guys see where this is going? That complementary thing? And then if we look at the oxygens, in both cases, these are combined oxygens. They're not peroxides, so it's going to be a -2 on each side. So as we go through this, we're starting to see, okay, the sodium went from 0 to +1. The hydrogen went from +1 to 0. So they're complementary to each other. So let's go back and think about our rules of what oxidation and reduction are. Oxidation is something where it combines with oxygen. No, we didn't have that. Lose hydrogen. I guess so. We could talk about that in a little more detail. Lose electrons. Okay, we're starting to get close now. Increase in oxidation number. All right. So let's look at that. If we increased our oxidation number, we went from 0 to 1. The oxidation number increased. Therefore, the sodium was oxidized. The hydrogen was reduced. So like we said earlier, where I repeated myself a few times, the reducing agent is the thing that is oxidized. The reducing agent is the thing that causes reduction, which means it's the thing being oxidized. The oxidizing agent is the thing that is causing oxidation, which means it is the thing being reduced. So sodium is oxidized, therefore the reducing agent. Hydrogen is reduced, therefore the oxidizing agent. This is tricky. I encourage you to stop this video right here, rewind it, go over it a couple times. This is not trivial. So within our different kinds of reactions, we talked about decomposition reaction. This is fairly straightforward in terms of what it is. We start with one more complicated molecule that breaks down into simpler portions. There's both redox and non-redox decomposition reactions. Combination reactions are the opposite of a decomposition reaction. Simpler reactants are combined together to make a more complex product. Again, we can have reduction or non-reductive combination reactions. The last two things that we're going to talk about are single replacement reactions and double replacement reactions. As I said earlier, depending on the resources you use, single replacement, double displacement, single displacement, and so forth. So displacement or replacement, same thing. So in a single replacement reaction, this is kind of like a really sad date. The way you could think about it is B and X walk into the bar together, they're dating, but A looks really, really attractive to X, and X leaves and runs away with, A leaves with X and runs away and leaves B by themselves. So this is a single replacement reaction. Someone single went in and someone different single came out. Redox reactions occur right when one element changes its compound and is displaced by another. So if this was an elementally pure thing, A on this side would have to have an oxidation number of 0. That's right, we know that rule. However, on this side now it's combined, so it's going to have a different oxidation number now. So redox chemistry is definitely occurring here. I encourage you, and this is right out of your textbook, go ahead and assign oxidation numbers to all of these. Determine who was oxidized and who is reduced, and by that, which one is the oxidizing reagent and which one is the reducing agent. The other kind of reaction we can get is a double replacement reaction, and this is a little more complex than the single replacement. Is we have two couples that go in and they leave with different partners. So they switch dance partners. We'll often see this with things like precipitation reactions or acid-base chemistry. These are really good examples of what double replacement reactions will be. So I would encourage you to pause your video here and go through and start working on these. Again, you'll have a lot of practice with this with your homework as well, but it's always nice to get a little extra while we're talking. So as we go through, we need to start determining which ones of these are redox or non-redox, and whether they're single displacement, double displacement, synthesis, decomposition, so on and so forth. So hopefully these are close to what you got on your try of it. The next type of equations that we're going to start talking about start utilizing the concepts that we talked about in chapters 1, 2, 3, and 4, and that would be ionic equations. Ionic equations are special. Oftentimes they are dissolved in water, and because of that we get to use an extra state of matter, which makes it kind of fun and cool. So we're going to be talking about aqueous solutions. Ionic compounds, right, are electrostatically attracted to each other. There's a positive and a negative. Not slightly positive, slightly negative, but positive and negative. And so they are polar, just like water is polar. And so they are going to be very attracted to each other and will break apart in water. The good example of this would be table salt, right? Table salt breaks apart in water. And please understand, I'm using the word break apart very deliberately here. We have to start making a distinction between the concept of dissociate and dissolve. We've mentioned this a couple times already in class, but in chemistry, there are certain words that have very different meanings, even though they might be things that you would interchange with each other in non-chemistry talk. To dissociate or dissolve to you in a common conversation might mean the same thing, but in chemistry they will mean very different things. To dissociate would be to break apart at the ionic bond level. To dissolve would mean to break apart individual molecules that were held together with other molecules. So one is breaking apart the atoms bound together of a molecule, and the molecule no longer exists. That would be dissociate. And dissolving would be, I have like a crystal structure of many of the same molecules, like make it some big solid, and that we dissolve or break up the interactions between the molecules, but the molecules still exist. That would be dissolving. There are some really good resource videos posted that kind of differentiate this dissolve dissociate, which is something you should definitely be comfortable with. So up until now, there are different kinds of reactions or equations the way we could write this. The one that we have talked about really so far is just molecular equations. This is how we've been writing equations this whole chapter, right? This idea of the atom, coefficients, the state of matter, this plus this yields this plus this plus this, that kind of thing. The new ones that we're going to talk about are total ionic equations and net ionic equations. And these will be in ionic compound situations, which hopefully makes sense. So the first thing we're going to talk about are total ionic equations. So let's look at an actual example. Here is a molecular equation. This is how we've been writing things. Real quick, let's go through and make sure this is balanced, right? We always know the first thing we should always be doing is balancing it. I see one sodium on this side, I see one sodium on this side. One chlorine, one chlorine. One silver, one NO3, one NO3. Now, when we're doing balancing chemical equations, it's really just a lot easier. NO3, that is a polyatomic ion, we know that. Just leave it together. It's not breaking apart. It's not like the N's are going somewhere and the O's are going somewhere else. It's staying as a unit. So it's just easier to say one NO3 and one NO3 instead of one N and three O's and that kind of thing. So a total ionic equation is going to be kind of like this secret language. So what we need to do is look at this state of matter that we have going on here. This is really important. Let's start with the NaCl. NaCl aqueous. This means that I have table salt, NaCl, sodium chloride, dissolved in water, right? Broken up into water. And what it's actually doing is it's dissociating in water, because we know that NaCl is an ionic compound. And ionic compounds in water, right, AQ, a special type of solution where the solute, right, the solution's in water, will break apart. So the molecular equation is kind of like the shorthand. It's a secret language, and it's a secret that you know, that I know, that you know, that when I see an ionic compound with a state of matter that's AQ, what's really happening is it's existing as the Na plus and the Cl minus. We don't actually have them bound together because they're hanging out and being broken apart by the water. So I have Na plus Cl minus, and then I have AgNO3, another one where it's an AQ. So I'm going to have Ag plus and NO3 minus yields AgCl solid. Well, I'm not aqueous anymore, so I can't break it apart. There's no secret language here. So this is just going to be AgCl solid, and then I have another ionic compound in solution AQ, so Na plus and NO3 minus. So total ionic equations are just kind of like the long-handed version of a molecular equation. We're no longer using the kind of secret language of what the AQ stands for. Um, and instead, we're going to write the whole thing out. Now, there's something special happening here as we look through this. Um, do you see some things that are on the reactant side that pop out exactly the same on the product side? Hopefully you're noticing that Na plus AQ went in and the exact same number of Na plus AQs came out. Same thing could be said for the sodium or the nitrate. So that brings us to our next type of equation, a net ionic equation. A net ionic equation is just going to be the meat and potatoes of the chemistry that occurred. What was the thing that changed? And to do that, we just take out things that remain the same. When something remains the same in a total ionic equation like this, like the Na plus comes in, the Na plus goes out. We call this a spectator ion. So net ionic equations, we remove the spectator ions and just write the chemistry that is occurring. We talked about this a little bit earlier when we were talking about that combustion reaction. We're going to talk a little bit about thermochemistry and energetics, and what we're going to discuss is this idea of energy as a product or a reactant. This is not the most perfect of analogies, and if you go further on in your chemistry career, you will learn that this is not the most elegant of analogies for this, but for the purposes of our class, it holds up pretty well. And the idea is that energy is required or expelled from a reaction, depending on what it is. Some reactions are what we call exothermic, and that means that the heat is being released from it, that when those bonds are breaking and reforming, it's actually in a lower energy state, so energy is being released. Often, this is heat is how we often kind of experience it. And so the energy could be in the form of light or something as well, but typically we see it as heat. So again, a combustion reaction, something exploding gives off heat. And when something gives off heat, we would consider that to be a product. So it would be an exothermic reaction. The opposite of that would be an endothermic reaction, and that would be a reaction that requires heat or energy to occur. And when that happens, oftentimes the resulting product feels very cold. So when we are talking about energetics and chemistry, it's not, we would never add cold something. We would be removing heat or having an absence of heat. So things don't get colder because we're adding coldness to it. What we're doing is removing heat. The best example I can give of this would be something like in a first aid kit, there's emergency medical packs where like you kind of break them and shake it and it becomes like an instant cold pack. That would be basically in that pack, when you break it, you're mixing chemicals and you're having an endothermic chemical reaction occurring. So up until this point, we've been talking about balancing chemical equations and the different kinds of reactions there are, the different types of ways we can write the equations. But now it's really important that we start talking about what I had mentioned earlier, where we start saying, well, what if I knew how many of one type of reactant I had, and that would be able to tell me how much product I had. We can utilize that help a way to measure it utilizing our balanced chemical equation, but we also need to talk about this concept of a mole or stoichiometry. So like we talked about before, you always need to have a balanced chemical equation before you would do any of this. And we're going to go back to using dimensional analysis as well. And the mole is a really important counting number. So if I were to tell you that I have a dozen eggs, you would know that I mean I have 12 eggs. If I told you I had a pair of shoes, you would tell me I have 2 shoes. So these words, dozen, pair, right? A ream of paper is 100 sheets. It's just a counting number or a counting word. It's a word that represents a certain number of something. And the mole in chemistry represents a certain number. It represents the number 6.02 times 10 to the 23. So it's a very big, big number, right? 10 to the 23 is very, very large. But it is a very useful number for us. It allows us to have very, very big numbers, and it allows us to have very, very small numbers, which is pretty much all chemistry is. And what we can do is the coefficients in a balanced chemical reaction can equate to the number of moles of whatever product we're looking at, or we could look at it in terms of saying like units, but we'll get into more in depth with the moles as you read through your textbook. So let's look at this redox reaction, this combustion reaction. Here's our methane again, and our oxygen producing CO2 and water. If we looked at this like a recipe, we would say, okay, I need 1 of these to every 2 of these, and it will make 1 of these and 2 of these. And what we're going to start looking at is kind of what we talked about earlier when we were talking about dimensional analysis and equalities. We could write a whole bunch of equalities based off of this balanced chemical equation. For every 1 of these, I require 2 of these. For every 1 of these, I get 1 of these. For every 1 of these, I get 2 of these, right? So we can make a lot of useful statements, a lot of useful equalities about this. And so here we have just some different ways we could rewrite this to represent different things. We could say 1 molecule of CH4 plus 2 molecules of oxygen gas yield 1 molecule of CO2 and 2 molecules of water. Or we could say moles, right? This counting number, this 6.02 times 10 to the 23. We could have 1 mole of carbon, or excuse me, 1 mole of methane plus 2 moles of oxygen, yielding 1 mole of CO2 and 1 mole of water. The conversion that's occurring here is 6.02 times 10 to the 23 molecules plus 2 times 6.02 times 10 to the 23 molecules of oxygen yields 6.02 times 10 to the 23 molecules of CO2 plus 2 times that. So it would just be like saying if this mole, instead of moles, we were talking dozens. 1 dozen CH4s plus 2 dozen O2s, that kind of thing. So it's just relatively simple math with very, very big numbers. So I'd like you to go ahead and try and utilize that balancing to try and figure out what we have going on here. We're told we have how many moles of oxygen gas, how many moles of this guy are we going to need to react with 1.72 moles of this guy. So what we have to do is first, before anything else, we want to make sure we have a balanced chemical equation. I see 1 carbon on this side, 1 carbon on this side, 4 hydrogens on this side, 4 hydrogens on this side, 4 oxygens here, 2 of them here, 2 of them here. So we have a balanced chemical equation. That's always the most important thing we first need to do. From there we go, okay, I was given that I have 1.72 moles of this. And we're going to use some equalities to get us to how many moles of oxygen we need. We know that if I have this many of my methane, what equality could we write? Could I say for every 1 CH4, I require 2 O2s? Yes, you could. So when we think about this, we have a 1:2 ratio of our methane to oxygen. So if I have 1.72 moles of my methane and it's a 1:2 ratio, I'm going to need twice as much oxygen for however much methane I have. That would give me 3.44 moles of my oxygen. So you can go ahead and start utilizing dimensional analysis to start helping you write these equations and solving these word-based type equations. And again, your homework will have lots of practice with this. The last concept that we're going to talk about in this chapter is a limiting reactant. A limiting reactant, the definition, right, as we say, is the reactant present at the end of the reaction in the least amount, or it's the thing that is completely consumed, is the thing that limits the reaction from going more. The analogy that we usually use for this would be if you're making sandwiches and you have 5 slices of bread and you have 4 pieces of cheese and 2 pieces of turkey or something to that effect. And you have to make your sandwich in a very specific way. Whichever ingredient or reactant you run out of first is the thing that limits how many sandwiches you can make. It is the limiting reactant, the thing that determines how much product could actually be made. So you will have plenty of practice with limiting reactants as well in your homework and in your reading. I'm hopeful that everyone will go through and read the sections that are necessary for chapters 4 and 5, and that when we meet again next Tuesday, that you will have lots of questions for us to go through as we keep moving through things. So keep on reading, keep doing your homework, email me with questions as you have them, and we will meet in Zoom next week.